Hello everyone, I'm Henry, and I'm going to present my joint work with Lizzie and Shuichi on a new circular bond for symmetric exponential time. As you can see, this is a merge talk with uh, another paper by Zeyong, who presents a simplified and truly uniform version of our lower bound. So I'm going to talk about the first half of this talk, and the second half will be done by Zeyong. In one sentence, what we do in this talk is that we prove a new circular bond by solving some problem called the range avoidance problem. Let's talk about the circular bond first. Circular bonds are just lower bounds against the non-uniform computation models such as circuits. And historically, it was one of the attacks for the P versus NP problem, because if you can prove a super polynomial circular bond for NP, then you can separate P from NP. Proving circular bonds has another motivation from randomization, and in this motivation, exponential size circular bond becomes important. In Pagliazzo and Wilson showed that if E, the class of problems with exponential time, if this class requires exponential size circuits, then we can prove P equal to BPP. That is, we can fully de-randomize BPP. So with this motivations in mind, what's known about circular bond? Unfortunately, not much. And Aurora and Barak's textbook called circular bonds complexity theory's Waterloo. So we are really bad at proving such circular bond. It's already known like 70 years ago by Shannon that if you pick a random function f on n bits, then it's very likely to require exponential size circuit. In fact, it likely requires size like 2 to n or n, which is nearly the maximum possible circular bond. So the problem is to find an explicit such function in a complexity class that's as small as possible. The first progress was made by Cannon, who showed that sigma 3e contains a language that requires near maximum circuit size. Sigma 3e is the exponential version of sigma 3p, and sigma 3p is np to the np to the np, which is like third level of polynomial hierarchy. So you can probably see that sigma 3e is a very, very huge class. And we are only able to prove exponential circular bonds for such super huge class. This was later improved by Michelson, William Chandler, and Watanabe to e to sigma 2. This is like maybe half level down in the exponential time hierarchy. But before our work, this is basically what we know about exponential size circular bond. So let's zoom in the exponential time hierarchy and see where we are. There are classes from e to np to e to sigma 2, all of which are very, very huge. But this only represents our inability to prove good circular bond. We know e to sigma 2 requires near maximum circular bond. And for the intermediate classes, such as sigma 2e, the second level of exponential time hierarchy, we have half exponential lower bound. So a function f is half exponential if f of n is something like 2 to n. This is proved by a win-win argument. So you do some win-win involving two input lengths, and in the argument you somehow need to compose f with itself. So we are only able to prove half exponential lower bound. This is super polynomial lower bound, so it's good, but it's not exponential. So ideally, we want to prove they require exponential size circuit. For the smaller class E to NP, unfortunately, we know very little about that. The current best world record is just 3.1n by Li and Yang, and even a superlinear lower bound would be a huge breakthrough in complexity theory. I also want to mention that under some randomization hypothesis, all these three classes are equal. So you can treat like S to E and ZP E to NP as just a randomized version of E to NP. Now we are ready to present our result. With Li Jie and Shi Qi, we proved that S to E with 1-bit advice requires exponential set circuit. So as you can see, S2E is the second class in our chain of exponential hierarchy. So this is proved by presenting a so-called single-valued FS2P algorithm for some problem called the range avoidance problem. We will talk about these notions later, but anyway, the main message is that some algorithm for something called avoid implies the circular bound that we try to prove. The F here means functional, which means our algorithm solves a search problem instead of a decision problem. Unfortunately, our algorithm only works for infinitely many input lengths, and this is because we use an iterated win-win argument. So our argument involves like around log n many input lengths, and the algorithm only succeeds on one of these input lengths. Fortunately, Ziyong Li came up with a simplified and truly uniform version of our proof, and he could get rid of the win-win argument and just win at once. You will see what it means when he talks about his proof. So he presented a single-value S2P algorithm for avoid that works for all input lengths n. Therefore, he could prove that S2E is not in something called IO set to N or N. The IO here means infinitely often. So this whole expression means that he can find a language in S2E that that on every input length will require near maximum circular bound. Instead, our function only requires near maximum circular bound on infinitely many input lengths. And by getting rid of the win-win argument, Ziyong also gets rid of the 1-bit advice. Finally, let me mention that all these results are relativize, so they hold with respect to every oracle. Now, after presenting our results, let's talk about the range avoidance problem. What is this problem? Why does solving this problem imply circular bound? In this problem, you are given an input circuit C from n bits to n plus 1 bits. And your output is a string of length n plus 1 that is a non-image of C. So I mentioned that this is a search problem, which means it has a lot of solutions. In fact, this is really a lot because half of the strings are non-images of the circuit. This problem can be seen as some empty version of pigeonhole principle. So imagine the inputs of C are pigeons, the outputs of C are holes. There are a lot more holes than pigeons, and the C specifies how to map the pigeons into holes. To solve the range avoidance problem, you just need to find an empty pigeonhole. There is a trivial FCPP to NP algorithm by rejection sampling. So we know that a half of the strings are non-outputs. So we can just sample a string. But it requires an NP oracle to verify whether the string is a non-image. So what we finally get is an FCPP to NP algorithm. This problem captures many explicit construction problems as shown by a very beautiful recent paper by Oliver Cotton. This includes Ramsey graphs, rigid matrices, two-source extractors, linear codes, and kind of important for us, hard truth tables. So it turns out that if you solve this problem, you also get hard truth tables, which means you prove circular bound. Pictorially, this problem it's something like this. So you have a smaller domain and a larger codomain. You have a circuit C that maps your domain into some range, and you want to find something outside this range. it turns out that you can design C such that all the truth tables with small circuit complexity are in the range of C. Therefore, if you solve the range avoidance problem for this C, then you obtain a hard truth table, which means you prove a circular bound. Let me get into more details. So there is the object called the truth table generator that will connect range avoidance and circular bounds. This generator takes a description of a size S circuit to its truth table. Turns out that when S is something like 2 to N or N, this truth table generator is stretching. Stretching just means that domain size is smaller than codomain size. So actually, this is just the proof of Shannon's lower bound. So somehow the maximum circular bound is near S, which is 2 to N over N. And you can see that if you solve the range avoidance problem on this truth table generator, then it will give you some truth table without size S circuit, which means you prove a near maximum circular bound. Let me also comment on the notion of single-valued algorithm. Roughly speaking, it means that so we consider like NP type algorithms, like algorithms that have a lot of computational paths. An algorithm is single-valued if every successful computational path outputs a canonical solution. So it means that two different computational paths, if both succeed, they should output the same solution. And of course, the solution should be valid. This connects search problem to decision problem. So it should output a single canonical truth table, and then this truth table will correspond to a Boolean function. Without this single value guarantee, you may have two computational paths that output two different hard truth tables. Then you cannot define a single hard Boolean function out of this. So we really need this single value notion. As an example, consider the task of generating n-bit primes. We know that many integers are primes, so it makes sense to consider the rejection sampling algorithm. You just sample integers and check, let's say using the AKS test, whether it's a prime. This is FCPP, but it's not single valued because when you plug in different randomness in your algorithm, it's likely to give you different answers. So for randomized algorithms, the notion of single-valued algorithms are more commonly known as so-called pseudo-deterministic algorithms. And what we are going to do is to present a so-called single-valued FS2P algorithm for range avoidance. I think we won't touch on what FS2P means, but Zeyong will present a so-called F sigma 2P algorithm, which is basically an algorithm that uses one existential quantifier and one universal quantifier.
Hi, this is Zeyong. For the second half of this talk, I'll show you a strategy for solving range avoidance using the power of sigma 2 computation. So let's start with a simple algorithms that solves range avoidance. For now, let's try to solve range avoidance on circuits C that maps n bit to 2n bits, and we are going to make use of an NP oracle. So start by considering a perfect binary tree. And for those who are familiar, this will be the GGM construction. And on the binary tree, every vertex would be an n-bit string. And on the leaf level, we're going to fill in all possible 2n-bit strings. So I'm going to enumerate all possible 2n-bit strings and fill them into the leaves one by one. So because of this, the tree size will be exponential in n, but we'll handle this towards the end of the talk. Now here is how the algorithm proceeds. We are going to invert vertices one by one. By that, I mean that, for example, let's consider these three vertices. I'm going to try to find a value for the parent vertex, such that when I apply the circuit C, it correctly evaluates the value of its children. And if there are more than one possible pre-images, I'm going to take the lexicographically first one. And here is just a statement that quantifies this lexicographically first requirement. And this can be done with the help of an empirical. And we are just going to proceed with this procedure from left to right and from bottom to top, trying to invert vertices one by one, until at some point we are going to hit a position where we fail to invert the vertice. This is because we enumerate all possible 2-bit strings at the leaf level, and many of them will be not in the image of the circuit C. Therefore, there is no way that we can invert that vertex. And therefore, at that point, we will be able to find a non-image of the circuit C. So suppose that we hit such a non-image, and I'm going to just assign bottom to the rest of the vertex in the remaining in the binary tree. And now the claim was that after I run these procedures, I obtain a useful tree. Why is this so? So first of all, the tree is unique because the whole procedure that I have described before is fully deterministic. And also the tree contains a solution that's exactly stored here, where we first hit a point where we fail to invert the vertex, invert the circuits. And because of this, this solution is going to be a single valued solution. And more importantly, this tree has this locally verifiable property. What does it mean? So suppose that someone shows me a tree and he claims that his tree is the unique tree generated by executing this algorithm. How do I verify that his tree is actually the unique tree? And to do this, for any time step t, we can verify the t step of the algorithm by only reading 3 vertices on the tree. So remember, this is when time step t equals to 1. I just need to verify that the value at the parents, when you apply the circuit C, correctly evaluates to the values of his children. And also there is this extra lexicographically first requirement, and here we need the help of a for all quantifier. But the morale is that to verify one step of the algorithm, you only need to read 3 vertices on the tree, despite the fact that the tree has very large size. And here is what happens when t equals to 2, t equals to 3, and so on. And therefore, in order to verify the whole tree, it suffices to use a for all t quantifier. And now the two for all quantifier can also be merged together, so we can actually verify the whole tree using one single for all quantifier. And most importantly, we will next show that this huge tree is actually compressible. To actually compress the tree, we need to look at a slightly different tree in the sense that we are going to traverse the vertices in a slightly different order. We are going to use the post-order traversal. It basically means that whenever you are done with 2 children of a vertex, you should immediately go to their parents. So here's what we do. Times that t, we invert this vertex. Times t equals to 2, we invert this vertex. And after we are done, we are going to immediately try to invert their parents. And after that, we proceed as follows. And again, at some point when we hit a place where we cannot invert the vertex, we are going to set bottom to the rest of the tree. And the nice property about this tree is that it can be decomposed into order n many subtrees. The high-level idea is basically because of the post-order traversal, these subtrees are going to have different heights. And moreover, for each of these single subtree, its value is uniquely determined by the value of the roots. This is because when you can just keep applying the circuit C to evaluate all the values of the tree, starting from the value of the roots. As such, to really store or encode the whole tree, it suffices to just remember the values at the roots of all these order n subtrees. And therefore, we can now write down a sigma2 statement, which says that there exists some winners that encodes the whole tree, such that for all time step t, the tree correctly executes the t step of the algorithm. And from there, one can then output the stored answer solution to the range avoidance. And this is basically how the algorithm works. So let me conclude with a few corollaries of our results. From using the algorithm that solve range avoidance, and we are going to prove explicit circuit lower bounds for these classes in the middle. And moreover, we also obtain a pseudo-deterministic constructions by making use of an NP oracle for all these important combinatorial objects. And that's all I have. Thank you for your attention.